Good morning everyone. Welcome to today's session. Today we are going to discuss biasness of a coin as a Bayesian model. Our goal is the transformation from frequentistic to a Bayesian style. Agenda of today's session: biasness in frequentistic view, analyzing a coin flip problem, interpretation of prior and likelihood and conjugate prior, designing a Bayesian model. First of all, we are going to model biasness. We know biasness means some favorability to either get one option or some other option. In the case of coin flip experiment, there are only two possibilities, like getting head or tail. So I am more interested in head. If the experiment most of the time favor head, then that coin is said to be biased. If the chance for getting head and tail are almost same, then we can say that it is unbiased. So in terms of probability, if it is 50-50 chance or 0.5 chance for both the events, then it is called unbiased. Now we are going to model this unbiasedness mathematically. Then we are going to apply our Bayes theorem to calculate the probability for head or tail, whatever your interest. So in coin flip experiment, biasness means favoring head or tail intentionally. To be specific, fix 1 for all head bias and 0 for all tail bias. That means if you get 1, that means all the events gives favorable to head. For this time I fix getting head as success. I am interested in only head. That is why getting head as success. All the time I get head in tossing a coin, I got biasness is 1 because it is more favorable to head. Now all the time I got tail, then I got tail probability is high. The full probability goes to tail, and so it is a 0 bias. 0 for tail and 1 for head, like that. Now we move on to the mathematical idea. Mathematically, bias is a function takes values from 0 and 1. See, I defined biasness like this. Bias is 1, that means full head. Bias is 0, that is full tail. So in this experiment, either I get full head, that is a maximum favorable thing if I consider getting head as success, and also 0 bias, that means I got full tail. There is no hope for head, like that. So it is mathematically a function between 0 and 1. The lower bound is 0, upper bound is 1. That means biasness is considered as a function from 0 to 1, or a function which takes all the values between 0 and 1, including the boundaries. That's all. The most suitable probability to model such function, as I told you, the function that takes values from 0 and 1 can be used to represent bias. That is a mathematical function. A probabilistic function to represent such a function is beta distribution. Then what is beta distribution? Any distribution can be identified by its probability density function. Here the PDF of beta distribution is beta of the lower bound alpha, upper bound beta is equal to gamma of alpha plus beta, sum of these bounds, divided by gamma of alpha into gamma of beta, into the parameter is here theta raised to alpha minus 1 into 1 minus the same parameter theta raised to second bound, that is beta raised to minus 1. Now this gamma function is nothing special. If this alpha and beta are integers, then positive integers, then gamma is simply factorial, nothing more. Gamma function is generalization of factorial function. Factorial function is defined only for positive counting numbers. If it is not a positive number or a fraction, we cannot use our ordinary factorial function, ordinary factorial definition. In that case, we make use of gamma function. That's all for this context. Okay, then bias is here our belief or prior distribution, because in coin toss experiment actually happening tossing the coin. On tossing the coin, I got either head or tail, nothing else. Then we know the prior information. There may be the possibility for intentional favorability to head or tail. It is considered as biasedness. instrument should be unbiased. If you are tossing a biased coin, then automatically it leads to some biased result. So unbiasedness is an important characteristics that we need to use a particular coin for coin flipping experiment. Okay. So the bias is our previous knowledge or prior distribution or a belief. Now we are going to discuss what is the likelihood. Okay. Before that, I will explain what is this beta function, what is its nature. Okay. I create this plot using Python. Nature of the prior distribution here, or beta distribution, it is depending on this alpha and beta. Look here, alpha and beta are 0.5, then I give a distribution like this, a U-shape one or cup shape one. When alpha is 0.5 and beta is 1, I got this shape. This is an exponential decay, something like that. If alpha is 0.5 and beta is equal to 2, again the same shape, but it become more steep. Alpha equal to 0.5, beta is equal to 3, almost same. When alpha is equal to 1, beta is equal to 0.5, or reverse, alpha value become high. Now look into this one, alpha is equal to 1 and beta is equal to 1. I got a horizontal line of height like this, same height. The left side gives the probability, that means the height is probability. So when alpha is equal to 1, beta is equal to 1, the probability is same for this range 0 to 1. Same probability, uniform probability. So it is uniform distribution. So beta distribution will become uniform distribution when alpha and beta is equal to 1. The same beta distribution becomes negative exponential distribution like this. Okay. When move on like this, at the end, look, when alpha is equal to 3, beta is equal to 3, what happened? It gives a bell shape curve, that means normal distribution. So depending on this alpha and beta, it takes different shapes. But remember, area under this curve should be 1 because the total probability is 1. That is for probability distribution. It takes any form, but area under the curve should be 1. So in that sense, we can see that beta distribution is the best choice. If you don't know about the properties of that function, you have only the limited knowledge about the starting point and end point, better option is beta distribution. It takes all the values between 0 and 1 and it takes this different distribution shape. So it is the combination of very much different distributions. From this picture, it is evident alpha and beta is equal to 1, uniform distribution. Here alpha is equal to 3, beta is equal to 3, it goes to a normal distribution shape, almost normal distribution. And also some negative exponential shape, also positive exponential shape. Okay, that is the reason why we are choosing beta distribution. Now come outcomes of coin flip problem. Come to that section. There is a likelihood while we tossing a coin, either get a head or a tail. Getting head or tail, either or, it's a possibility. There is a likelihood. The likelihood is from our experiment, prior from biasness. Okay. Get either head or tail in a trial of single flip, coin flip. So the best probability distribution is binomial. True or false. Getting a hot dog or not getting a hot dog. Either caught by police or not caught by police. Hit the target, not hit the target. Defective or non-defective. All these are only two cases, binomial. We use binomial distribution. So the binomial distribution is captured by this formula. The binomial distribution has two parameters mainly, theta and n. This y is the variable. Binomial distribution of y under theta and n is given by, this is combination ncy. Theta raised to y into 1 minus theta the whole raised to n minus y. ncy theta raised to y into 1 minus theta the whole raised to n minus y. I think in our regular classes we use x instead of y because usually y is our sample. In that sense we are using y in the place of x. If we are x in place of y, we got ncx p raised to x into q raised to n minus x, and also there is p instead of theta in mathematics literature. We are going to interpret in terms of machine learning languages. That is why I use theta as the parameter for probability distribution. Capital N is the total number of trials and y is the variable, like that. Now the probability distribution addresses, this binomial distribution addresses the distribution of outputs So binomial of y with theta n is the likelihood distribution. See, the simple coin toss experiment, we use the belief as our beta distribution, and also the experiment, that is getting head or tail, that is by binomial distribution, and so we got prior distribution and likelihood distribution. Prior, belief, and actual coin toss experiment, the possibilities, that is our likelihood. So we got prior and likelihood. Okay. Now we think about what about the likelihood distribution. Likelihood distribution is like this. Here also, I repeat, I am considering getting head as success. In the case of one toss, I consider only one toss. The theta is equal to 0.25. That means probability for getting head is 0.25. Look here, y is number of head. Here I have one head. This probability is 0.25. See, theta is 0.25. Total probability should be 1. So the probability for 0 means getting 0 head. That means tail, one tail. That is 0.75. Like that. When we n increases, we got different shape. Also theta changes, it gives different shape. Now look into the last row. When we repeat the experiment 4 times, then theta is equal to 2.25. Getting a head is a probability for getting a head is 0.25. It's very low. Now look, 0, getting a tail is 0.28 something. One head, it is about 0.4 something. Two head, it is again very low, it is less than 0.25. Then 3 head and 4 head, the probability for 4 head is very low. That means out of 4 repetition, getting all 4 head is very low. If we put theta is equal to 0.5, what happened? Theta is equal to 0.5 means 50-50 chance getting head and tail. 0 means 0 head. So for all tail, the probability is very low. And 4 head, that is the all head, again the probability is very low. 2 head and 2 tail, 50-50, that is maximum. When we join these points, we got these spikes, we join the spikes, we got the normal distribution. So 50-50 chance is normal. 50-50 chance is normal. That is unbiasedness. So normal distribution is also an unbiased distribution. That's another interesting connection. So when theta is 0.75, that means the more possibility for head, in that case it is skewed to the right. More head, probability for more head increases. Probability for 0 head, that is all tail, decreases. So this probability is very much affected by, this graph is very much affected by this probability. Okay. Now it's a jetpack. We occasionally use, even in the case of Bayesian model, an important concept, the concept of conjugate prior. Okay. In Bayesian theory, the concept of conjugate prior is very useful. It states that in Bayesian settings, prior and posterior follows same distribution. Conjugate prior means nothing. If a prior has a particular distribution and it is conjugate prior, then automatically the output, the posterior distribution, is also the same distribution of the prior. That is called the conjugate prior. Then the prior is called the conjugate prior. Beta distribution is a conjugate prior. Now look into this sentence. Beta distribution is a conjugate pair. That means if beta is our prior distribution, its output, that means our posterior distribution is also beta. So the calculation is very simple. That likelihood function has no impact. There is no change will happen in the distribution. That is the idea. So the Bayesian posterior is also will be beta distribution. The case of normal distribution, we have the same thing. Normal distribution is again conjugate prior. That means if the prior distribution is normal or Gaussian, automatically the posterior distribution is Gaussian, the same shape. If the input, the prior knowledge is Gaussian, then automatically the output, that is the posterior distribution, is also Gaussian. This is only valid if the conjugate prior idea is existing. So conjugate prior is a nice idea that help us to calculate posterior distribution without much difficulty. So it is called a jetpack because all other activities are not necessary. We got the idea about the posterior, we just move on to we just jump into posterior, not waste much time in the workaround. That is the idea of the use of the idea of conjugate prior. Okay. Now joining the nuts and bolts, we know the prior distribution and also now the likelihood distribution, mix it, and also make use of the conjugate prior distribution, then what about the result? Okay, now let us join the prior, likelihood, and use conjugate prior concept to define the posterior. So this is our Bayes theorem. Probability for theta under this D is equal to probability for D under theta into P of theta by the evidence P of D. Now I am going to avoid this denominator. Denominator is P of D. P of D is actually the marginal distribution. We make use of this P of D to make this P of theta given D, that measure as a probability distribution, because a probability distribution must satisfy two important properties. One is each value of the distribution is positive. Second one is the total of the distribution should be 1. To make it calibrated or make it normalized, we use this denominator. If we exclude this denominator, equal to will change. In that case, we use this proportionality. Or in another sense, this P of D, the evidence is just a proportionality constant, nothing else. So I avoid this P of D. In that case, it becomes proportional. So we have P of D given theta into P of theta. But we know what is prior distribution. Prior distribution is our gamma distribution. Beta distribution. And the likelihood distribution is our binomial distribution. We write the corresponding PDFs here. P of D given theta, likelihood function, that is our binomial distribution, NCY, theta raised to y into 1 minus theta raised to n minus y, into, see this one is beta, gamma of alpha plus beta by gamma of alpha into gamma of beta into theta raised to alpha minus 1 into 1 minus theta raised to beta minus 1. Then see, here we have theta raised to y. Also another expression theta, we can combine this by using the law of exponents. So here theta raised to y plus theta raised to y plus in the power alpha minus 1. A raised to m into a raised to n is equal to a raised to m plus n. Use that. So instead of this constant NCY is a constant, it's a combination. Again we know these gamma functions are generalization of factorials, so it's again a constant. So this equal to some symbol can be replaced by proportionality and avoid these terms. To make it simplify, I avoid these constant terms. So equal to changes to proportionality. Now apply rules. Theta raised to y into theta raised to alpha minus 1 is theta raised to alpha minus 1 plus y. I take this alpha minus 1 first, that's all. Again apply the law of exponent in 1 minus theta raised to n minus y and 1 minus theta raised to beta minus 1. That is 1 minus theta raised to beta minus 1 plus n minus y. 1 minus theta raised to beta minus 1 plus n minus y. Now this alpha minus 1 is here, that is in prior distribution, and also beta minus 1 is in here, this again in prior distribution. I can rewrite this alpha minus 1 as alpha in prior, this beta minus 1 as beta in prior. Then what happened? This alpha minus 1 can be replaced as alpha prior and beta minus 1 can be written as beta prior. Then this can be written in this form, beta of alpha prior plus this y comma, here the power is beta minus 1 is beta prior, so beta prior plus n minus y. So what happened? This P of theta, the prior distribution is a beta distribution. Now we got the posterior distribution is also a beta distribution. Definitely there are some constants, that is why I use a proportionality constant. Okay, so the posterior distribution is proportional to a beta distribution, provided our prior distribution is beta distribution. What do you get now? You just model a Bayes approach to an unbiased coin. If a coin, the unbiasedness of coin, or the biasness, more clearly the biasness property, that is modeled here in the terms of prior distribution, and we diffuse it into the coin toss experiment. So we got the posterior distribution. When we use the Bayesian model, you need not to specify it is unbiased, because unbiasedness is addressed here. In a coin toss experiment, biasness is incorporated in prior distribution, and so it tells everything about the model. You need not to specify is unbiased. This unbiasedness, the biasedness property is modeled mathematically and use beta distribution, and it is diffused here, and so a coin, you need not to specify unbiased. You can avoid that word. You just call it as a Bayesian model of coin toss. A Bayesian model of coin toss experiment is always unbiased. It is incorporated there with the help of distribution. You compare this with our Lagrange multiplier method in linear algebra. What is the Lagrange multiplier method? There is an objective function, we have to maximize or minimize it, but there is a restriction that is called the constraint, subject to that constraint. Then what we do in Lagrange multiplier? We add that constraint into the function itself with a proportionality constant lambda. It is called our Lagrange multiplier. Then we solve it. The constraint, the restriction is incorporated in the function. The Bayesian model will do that. The Bayesian model incorporates the constraint into the original function. The constraint is here prior distribution. It incorporates prior distribution into it. But remember, the Lagrange multiplier method is applicable only for linear system. But this is in the probability system. There is no restriction. Linear, non-linear restriction is not here. There is only one restriction, that is the property of distribution, either continuous or discrete, like that. So we can compare the performance of Bayesian model to our Lagrangian Lagrange multiplier method in linear algebra in optimization. Okay. Advantage of this, I already told you. Now the condition unbiased is incorporated in the posterior distribution. The unbiasedness condition is here, it is incorporated in posterior. Okay. The sampling from posterior distribution. I take this distribution, both the prior and likelihood, and create a posterior distribution using our Bayes theorem, and I plot it. Now look into the plot. You can see this: 0 trial, 0 heads, nothing happened. But there is 3 distributions. One thing I would like to say, that area of this distribution is actually posterior distribution. You just consider the area covered by distribution. That is my posterior. Here we have red, green and blue. That means I am using 3 combination of priors, 3 priors. That is it's a mixer model. I am taking 3 priors. Then I got the posterior distribution like this, spread of these 3 distribution. I 1 trial and 1 head. I repeat the trial only once and I got 1 head. Then this again it contains 3 models. It's a mixture of 3 models. Again mixture of 3. 2 trial, 1 head. 3 trials, but I got 1 head. Again mixture of 3. Then I repeat the trial, 4 trial, 8 trial, 15 trial. As the trial increases, what happened? The performance of this different distribution, this mixture model changes. Even here also we have all these things in the normal form. It come to normal. All distribution come to normal. Again it is close to each other. Again here also we have 3 distribution but close to normal distribution. Here also we have 3 distribution. Then what happened here? I repeat the experiment 150 trials, 150 times. I take 48 heads, almost equal condition. So I got only 2 distributions, two Gaussians. Output becomes a combination of 2 Gaussians. This experiment will tell you an interesting fact. Suppose you are in a dilemma in taking a decision. You ask opinion for many people. It is something like that. You ask 3 people what I have to do, then they give this in different suggestions. So this is your posterior distribution from there. This is your decision, this area of this graph. Then we repeat this means your experience repeats. You do have this experience in many cases, 150 trials, in 150 different occasions you this, then you got this idea, only 2 distributions enough. That means in order to take a decision from your own experience, you come to one thing. You need not to ask many people. Ask 2 people. But what about that 2 people? That 2 people will be normal. It's a nice thing. Whenever you have a problem, don't ask to solution to many people. Ask only to those people who are normal. You have to take suggestions from normal people. That is the observation. See, we start with many distributions. Unfortunately, they give different suggestions. That is why this is a uniform, this is again negative exponential, this is almost normal. We got different types of suggestions. So area of all these three graphs constitute to your decision. It is not that much sharp and precise, and at last you come to the conclusion that from your experience, more experienced, you don't ask many people, only to normal people. It's a nice thing. So it is important takeaways. A Bayesian model of a coin flip problem will adapt unbiasedness, that we have seen. A coin flip problem is the simplest version of a mixture model, because we start with three different beta distributions, then it finally leads to a mixture of two Gaussian distribution. Coin flip experiment is make use of the mixture model. Bayesian models will work like constraint optimization operations such. I explained it. A beta distribution can be used as a prior to represent probability models for functions with only non-boundaries with varying values. It is the importance of using beta distribution in the case of selecting prior. Then a uniform distribution is the best, that is my observation, a uniform distribution is the best prior to model functions with non-boundaries but equal probability to choose values. All the values will chosen equally likely. In that case, instead of beta, you can use uniform distribution. Beta distribution is used because here we cannot say they are equally likely. Okay. Last one, the conjugate prior and proportionality of probability will reduce model prediction. That means the conjugate prior, the use of conjugate prior will reduce the work. Okay. The proportionality of probability will reduce model prediction, because once you know the prior distribution is a conjugate prior, then the posterior distribution also will follow the same distribution. That knowledge will reduce our labor. That's all. Okay, thank you very much.